Hey there! In this video, I will try to explain intuitively why when doing complex multiplication, the angles are added. The addition of angles can actually be explained easily if we use the polar form, but here I want to take a more untraditional approach. So we will only use geometry, and you do not have to know anything about the polar form to understand this. So let's take an arbitrary complex number z here. This is z. It has an imaginary part and it has a real part. I find it useful to think of complex numbers as vectors sometimes. So let this vector z have a magnitude c. And this is the circle with radius c, which represents the tips of all vectors that have the same magnitude c. Now let's say we want to multiply z by another complex number a plus bi, so z times a plus bi equals a times the vector z plus b times the vector zi, right? I will call this resultant vector r. And again, I'm representing this as a vector. Now, how can we show this vector r in the plane? The term a times z is a vector, and the term b times zi is also a vector, right? And they are added together. And we know how to add vectors. A is a constant here, so a times z is a stretched vector which is in the same direction with the vector z. So let's draw a times z. A times z. To draw b times zi, we know that zi is the 90 degrees rotated version of z, which the definition of I explains. So now let's draw zi. This angle is alpha. Zi has the same magnitude with z. It's only rotated by 90 degrees, so this is 90 degrees. This is also 90 degrees. So this is alpha, right? Okay, so b is again a constant, and b times zi can be represented as a scaled version of the vector zi represents. So I will draw b times zi with a different color. This is b times zi. b times zi. Now we must add up a times z and b times zi. Complex number addition is the same here with vector addition, and the vector analogy I'm using here is working because of this, and I hope it will help to better understand the angle addition property that we are getting closer to show. At this point, I would like to draw the vector a plus bi, just so we can see what we are multiplying z with. This point is a, this point is b, and this will be the tip of the vector which represents the complex number a plus bi. So let's write here a plus bi. Adding az and b times zi will give the resultant vector r. A times z is alpha degrees rotated from the vector a here. Let's draw the vector a by the same color with a times z. This is the vector a. You can see that a times z is alpha degrees rotated. And let's draw the vector bi with blue. This is bi. and b times zi is alpha degrees rotated from bi here. This is alpha. And both counterclockwise, of course. Remember, the vector a plus the vector bi gave us a plus bi. Now, rotating both these two vectors alpha degrees and adding them gives a resultant vector r, which is rotated alpha degrees from a plus bi. Just imagine we rotated the whole plane alpha degrees and do the same addition. A plus bi is the green vector right there, and the resultant vector would be something like this. Alpha degrees rotated counterclockwise. So here you might argue, well, this is not the same addition because the magnitude of a plus bi have changed when we multiplied each one with z. And yes, their magnitudes have grown, but in the same ratio. So just imagine rotating the whole plane, the vectors a and bi by alpha degrees, and stretching the vectors a bit by the same ratio, and then just adding them together. The resultant vector is also the alpha degrees rotated version of the previous sum. So by multiplying a plus bi by z, we ended up adding the angle under a plus bi and this angle alpha under z. This was a geometric approach to this angle addition property, which required only some basic vector addition and scalar multiplication knowledge. I haven't seen this approach elsewhere and wanted to share it. Hope you enjoyed.